the other homework assignment was when I let these two balls go at the same time, which will win the race? The one with the greater average speed or the one with the less average speed? And we'll say that this one is A, and we'll say this one's B. Is A, and his B. So you put down what your answer is. The question is not which is going faster at the end. And the question is not even which has the greater average speed. The question to be answered is what? Which wins the race? Which gets to the end in the shortest time? The fast one or the slow one? Okay, let's try this one. Here we go. Which has the greater acceleration? Same. Same. No problem, right? Okay, good. Now, for the balls, how many people haven't thought about this at all? Stand up. If you have two people running down the street and one has a greater average speed than the other, the one with the greater average speed should get there first, yeah? Yeah. Any problem with that? No. Then there's no reason to even show that, is it? No. Good, okay. Now, today's lecture is Okay, I tell you what, 25 cents each. 25 cents.
You're paying us?
Yeah, you pay to see.
Oh, I thought you were paying us.
Yeah. Okay. Here we go, gang. Here we go. Ain't that nice? Any question? Counterintuitive, though, isn't it? It's counterintuitive because you know that they'll both intuitively have the same speed over here. When we get to energy, we'll bring this out again. And we'll talk about potential, kinetic, then even more kinetic, but up here, same potential, kinetic. So they'll have the same speed going off the edge. And so a lot of people answer the question same, because they intuitively know it's the same speed. But trick questions are always what? Not always, but most often what? Where you're answering the question that's not asked. And this is which has the shorter time. And if you want to do it by the distance is the same for both, but one has a higher average speed, therefore a lesser time. And so you can let the equation guide your thinking. Small time when you have a high speed. And there's certainly more average speed down here. Let's suppose up here the speed is, let's say 2 all along here, okay? Let's suppose over here it's 4 all along here. And it's 2, and it's 2. 2 centimeters per second, whatever, okay? What's the average speed from here to here? 3. Now 3 is still greater than 2. What's the average speed going up?
3.
It's going to be 4, 2, it's going to be 3, and that's even greater than here. So all along this part of the track, it's going faster than it is on the top. So it wins. Greater average speed, shorter time. Yum, yum. Okay, today I'm going to attempt Newton's 3 laws on 1 class period. I would take a lot longer in a regular class, of course. What do I use this for? Inertia, yeah. You can't have a pointed head. Okay, I'm looking at the yellow one. How can I see the green one without touching anything? Yeah, just turn it around. Didn't work. You get the idea. I'm not going to keep doing it over and over again. But if you had a flatter head, you could turn around and there it would be, okay? It's like turning your soup. You know, you go to the restaurant and you're eating some soup and there's a fly right there. Now you got a fly and it's kind of buzzing around there. You don't want to eat that fly. Well, what do? You take your soup and you turn it around, right? But when you turn it around, well, what happens? The fly stays there. So you have to eat the fly, okay? Or coffee, you know, you turn the cup and the coffee stays still. A body at rest tends to stay at rest. And then we know the idea that a body at rest tends to stay at rest. Here I've got we talk about mass, we talk about weight. Here's a piece of block right here, this block wood. This block wood has mass, doesn't it? To say it has mass is to say it has inertia, right? And to say it has inertia is to say it has what? A tendency to stay where it is since it's at rest now, right? So what I'm going to do is I'm going to pull the cloth, not slowly, I'm going to pull the block very, very quickly, and I'm going to test your knowledge. I'm not going to pull like this. I'm going to whip it. And when I whip that block, what I want you to do is I want you to make a prediction as to whether the block, 3 choices, stays essentially where it is, 2, recoils onto the floor, and 3, moves in the direction in which it's pulled. Check your neighbor and make a prediction. Okay, gang, here we go. How many said stays essentially where it is if I pull quickly? How many say no, recoils onto the floor, Newton's third law? How many say it comes along this way because you pull it this way, showing that force and acceleration are always in the same direction? How many? Here we go. Number 3 wins. There is force provided by the staples.
What's the coefficient of friction there?
Coefficient of friction is infinity. So there's a whole variety of these things. One is I lie on a table and have put a big 60-pound anvil. Oh, 60 pounds, you gotta know what that means. Several kilometer mass anvil. And someone takes a sledgehammer and hits it, and that's a good one. That's a good one. And the body at rest tends to stay at rest, and you're perfectly fine underneath there. You know, there's a limit, of course, but I haven't seen it. I did have an unfortunate experience of I used to allow students to come up and do that. Well, come on, it's just, the anvil's that big. The worst could happen is that they miss it. It's not that they might hit it too hard or hit it too low. It's that they might miss it, but who's going to miss an anvil? Come on, you know. So I had a guy one time, I guess my 4th year in the teaching, and I was lying there. He had the big sledgehammer, boom. And someone says, hit him again, harder. He's okay. Boom! And he missed.
Oh, my goodness.
But he didn't miss me. Do you notice that one of my hands is a little bit different than the other? Yeah, really, scouts on it. He broke a couple of fingers in my right hand. No, my left hand. That's the one I write with. And so that learned that now I'm ambidextrous. So, yeah, he missed the anvil and hit my fingers, smashed my fingers up. Yeah, and I was in a cast and everything. I went to see the president of the school a couple of days later, and he said, Hewitt, what happened to your hand? I says, Harry, these students are getting out of hand. I said, Scout's honor. I was assaulted in my class with a sledgehammer, and he broke my fingers. So now I have a practiced assistant come up and do it. I have someone that sits in the class, pretends he's a student, and then invites someone. He comes up and he hits it nicely. But that's a nice one. What a wonderful course to teach, huh? How would you like to teach keyboarding? I mean, we have the most delicious course of all to teach. And furthermore, it's even further enhanced because people come in expecting it to be the killer course. And we turn them, no, it's not the killer course, it's the delightful course. The course that tells you what the connections are in nature and where you fit into nature and how beautiful nature is if you look at it correctly. And that's what we get paid to do, over and over and over. And isn't it true that every time we teach it, we think of something new we didn't think before? And that's a beautiful profession to be in because we keep enriching ourselves all the time. That's just wonderful. But anyway, you guys know that. Now, more on Newton's laws. I didn't even state them. You guys know what Newton's. First, what? Body at rest tends to stay at rest. If it's moving, you're going to keep moving anyway unless you mess with it. And you can talk about cannonballs firing. And in the old days, this distinction between mass and weight, I want to talk about that. In the old days, you used to wonder why a cannonball will keep moving once it got outside the cannon. And the whole idea was that it must have parted the air, and the air in the back squeezed in and squeezed it along like ivory soap in the bathtub. And that wasn't that long ago that it was just kind of straightened out by Galileo and Isaac himself. And then we make a distinction between mass and weight. That's one of the distinctions we made. So far, we've made one big distinction. What has it been in the course so far? An important distinction. It's been velocity and acceleration. And to get those two distinguished is a big task. A very big task. And it might be that your students will go all through the semester and still not really make that distinction. Hey, it's okay. They don't have to get everything. And here's another distinction, that between mass and weight. Which is more fundamental, mass or weight? And what do I mean fundamental? You know when a kid asks a question, why? And then finally you get to a point and you can just say, well, that's because that's the way it is. Well, that's fundamental. You know, why do objects have a mass? Someone say, why do objects have weight? What do you say? Because they're interacting with a gravitational field.
Then when they ask what is gravity, then you really stop.
Oh, gravity? Well, we don't know what gravity is. Do you know why? Nobody back then really knew. Hey, there was a time like this. Do you know how you get from one part of the country to the other? Get in a great big aluminum bird and fly over the weather. True or false? Begins with an F. Couldn't do that then. There was a time you couldn't do that. And there was a time, back then we didn't know what gravity was then either. And right now, ask a physiker, hey, how come that falls? Honcho physiker, Nobel type physiker. What's the physiker got to say? DBK. Don't be knowing. And how come we don't be knowing? Hey, what did we know back then? Not so much. A lot, but we didn't know that. Here's a nice distinction between mass and weight. This proof the Earth is rotating. This is the first time I've done it up here, like this. Brian suggested I try it this way. Okay, these two objects have mass, how much stuff, and they have weight, the interaction of the stuff with the Earth, a force. So weight's a force, mass is a scalar quantity, it's the amount of stuff, the amount of inertia. Okay, what I'm going to do is I'm going to take this and I'm going to pull it slowly, 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 and either this string or this string is going to break. And you know which one's going to break, and you're going to check that with your neighbor and make your prediction too. If I pull slowly, 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 the top or the bottom. Or I'm going to pull it quick and I'm going to snap it down. I'm going to pull it down, I'm going to pull my hand down with an acceleration greater than 10 meters per second per second. What's this going to do? All of a sudden go along with it? It's lazy. The word lazy in Italian is what? Inertia. It has inertia. So we know that if I pull this slowly, 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 which one will break first, gang? Top? It is the top. And over here I pull that like that at the bottom. Now, what does that distinguish? In which case was weight apparent? In which case was mass apparent? When I pull it slowly, 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 didn't I set up a tension in here? Don't I have a tension? Isn't that tension up here too? So, even Steven, either one. Except, even if I didn't pull it, it'd be what? A tension in here due to the weight of the object. So when I pull this down, this one breaks because we have the weight, and then Brian has it set up so this string is just about to break anyway with this particular mass. Okay? And so a little extra pull, and because of the weight, the top string breaks. If I whip it quickly, what's at work? Weight or mass? Check your neighbor. But I think this is nice for distinguishing between weight and mass. When you pull it quickly, boom, the mass of the object resists motion so the bottom string breaks. When you pull gradually, the weight of the object is giving an extra tension on the top to begin with, and the two combine. So weight will determine whether one breaks, mass determines the other. A nice way to distinguish between the two, I think. Here's another one with a hammer. Have a massive head. And if I want to tighten the hammer head, remember when you guys were little kids and it was a little bit loose and you were going like this? And Uncle Harry came by and he said, no, child, you don't do it like that. You should tip it up like this. That's how you tighten the hammer head. And you said to Uncle Harry, HC. And Uncle Harry said, well, this has considerable mass. To say it has mass, to say once it's moving, it'll tend to keep moving. And it goes right on there and moves on there tighter. Try it again. And so the mass of this thing, the tendency to keep going, will make the hammerhead come down tighter against the handle. And a nice application of that has to do with your height. How tall are you? On your license, it gives your height. Is that a morning height or a night height? And you guys know that you're taller in the morning or the night? In the morning. In the morning, you're taller than you are at night. And a lot of your students don't know that. A little bit or a lot? Answer begins with a L. No? A little bit or a lot? Quite a lot. Yeah. And it turns out why? Because when you're walking around all day long, what are you doing? You're like the hammerhead. You're jogging down. What happens to the little bones in here? They all get tighter and tighter and tighter. Do you ever see guys jogging and one says, well, let's go, Harry, let's take a run. They take a run, boom. At the end of the day, they come back, they're like this. You know that. And then at nighttime, you get into bed and you straighten right out, get up in the morning, boom, like that. Now here's what I want you to try, or have your students ask to do this. Find some part of the room. Okay, right here. Let's suppose that's as high as I can touch, okay? I'll tell you in the early morning, you probably touch up here. And at nighttime, I can't make it. It's appreciable. Try it. It's appreciable. Try it tonight. And tomorrow we'll have a piece of paper around here. I'll have a little check mark whether you noticed it to be higher, taller, or shorter. It's significant. Yeah?
A variation of that hammer one is the ketchup bottle. You know, you see guys doing that.
That's a good one.
You should be accelerating the bottle the other way to get
Oh,
ketchup.
oh, wow, I never thought of that.
It's
yeah.
stupid to do that.
Yeah.
Those guys don't know physics.
You've got your French fries there, just go whoop. Okay. Yeah. Hey, that's nice. That's nice. I like that. I like that. As a teacher, I have an advantage over my colleagues in that I started school late. I started school at the age of 28 years old. And at 28 years old, I started to learn my physics. And at that meant that I was completely ignorant about physics. The idea that there were connections that all would hold together. I was completely ignorant about physics when I was a young adult. And I think that gives me a great advantage over others in being a teacher, because I really know what it's like not to know anything. And I'm not talking about as a child. I mean as an adult. And I got my physics start when I was painting signs in Miami, Florida. I'm from Boston originally. And did you guys ever paint signs in Boston in January? On the shady side of the street? You know what I'm talking about. And the paint gets what? Today we say viscous. What did we say back then? Gummy. Yeah, and you had to kind of it's terrible painting signs in Boston. So I went to Miami to get away from the winter. And this Scout's on a story. And it was in Miami. I got a job painting signs. And I just got hired. I was lucky to get hired. Didn't have much money. And I got hired, and I was told, oh, you're going to have to paint with this fellow over here. His name was Burl Grey. And the other guys didn't want to paint with Burl Grey. But I was the new person on there. I had to paint with Burl Grey, because there was a rumor going around about this guy. And I found out firsthand the rumor was true. Yeah, he was one of them. You know what I mean? He was one of them. And so I was painting with Burl Grey, and I started to become one of them too. Started at least. And he was accused of being, of course, an intellectual. Yeah. And yeah, you know how they are. You know, hey, the intellectuals don't cut it in the sign painting circuit, because intellectuals talk about ideas and things like that, philosophical things, you see. And the regular guys would talk about sports, you know, cars and their fantasy sex lives and things like that. Well, Burl talked a little bit about those things, but most he talked about ideas. And he blew my mind. And that was my first intellectual. And whoom, that was something. I went to high school. I was good at drawing. And the high school counselor told me that I wouldn't have to take any academic courses. So I didn't. And I got into sports. I get into boxing and all that sort of thing. In the boxing circuit, I didn't really meet any strong intellectuals. But when I was with Burl Grey, he lit my fire. And he asked me questions that just got me really, really excited. And one of the questions he asked was, if you have a phonograph record, do you guys remember those? Down in San Francisco, we have a place called Tower Records. And you go inside there, and guess what? There's not a single record in there. I was in there a couple of weeks ago. Hey, where's your records? We don't have any records. What do you have? Tower Records. What's the records? So they have all CDs now, okay? But back in the old days, they used to have records. I think you guys know what they are, right? About this, a little bigger, small than this. And these things would rotate how fast around? to see if you know. 33 1/3. Ah, oh, you were there, Jim. You were there. Okay. Do you remember 78s? I have 78s. Ooh, how many know about the other one? No, not here, not this group. Let me tell you what it is. 45s with a big hole. Yeah, okay, okay. The rest, they don't know what we're talking about, right? Okay. Anyway, Burl asked the question. He says, well, when your wreck is rotating, if you put a marble on, it'll roll off the edge, won't it? Or if you put a sugar cube on, it'll slide off the edge, won't it? He says, what would be the direction of slide? Now, how do you think the average sign painter responds to a question like that? Who cares? So Burl said, well, let's make it interesting. And this is what he did. He really did this. Let's make it interesting. We'll put a stick on there, and it will turn with the record, see? And so let's suppose you got a stick holding everything, and the stick rotates with the record, right? Now, let's suppose you put a sugar cube on here. The sugar cube's going to slide off the edge. So as it's sliding, it's going to, it's going to go like a spiral, right? And when it comes back to here, it's either going to go like this, or it's going to go like this, or it's going to go like this, or it's going to go like that. Let's call it A, B, C, D. It's going to take one of those paths, let's say, huh? Well, what path do you think it will take? Check the person sitting next to you and talk about it. How many say A? How many say B? How many say C? How many say D? How many say, haven't given me enough time? Well, I knew what I was going to do because Burl was always asking these puzzles, and I was really intrigued with this guy. And so I wanted to come up with the answer, and I knew what I was going to do that night. That night I was going to go home. I had a record player. And I was going to put something heavy on there, and put a bit of sugar cube on, and let it slide off. But I was together. I'm going to put talcum powder on the floor. Now, why the talcum powder, gang? Why? Why the talcum powder? Hey, I knew enough to know that your mind plays tricks on you. We found out about that yesterday, right? Okay? Your mind plays tricks. So the talcum powder will show the path, see? And so, man, when I get home, guess what I did? The same thing you guys did last night. You got into other things and you forgot about it. And I never did it. And the answer to this thing was like a secret from me until I went to prep school a year and a half later. And in prep school, I learned about it, and boom, I had it, and the secret was revealed. Now, I can tell you guys, because you're teachers, can you keep a secret? Do you want to know the answer? Can you keep a secret? I can too. I'm not going to tell you. Burl didn't tell me, and I'm glad he didn't. And he didn't tell me because he didn't know the answer. And maybe I don't too. You don't know, but I won't tell you. Sorry. And then we were doing things like this. We're on stagings. And Burl's over here, painting away over here, and I'm over here. I was a little lighter than Burl. And Burl's weight acting down like that. I'm a little bit lighter like this. This is the staging, billboard, painting, get it? Hooks at the top. And Burl starts twanging his rope. So what are you doing?
Is Burl still with us?
Hang on about Burl. Hang on, I get the punchline's coming up. Punchline's coming up. Well, let me just tell you the punchline. I lost track of Burl Grey. And in my exploratorium class, just this last semester, I was talking to a private detective. And I told him how I can't find Burl Grey, and I'd like to find Burl Grey. He's been the biggest influence of my life. He says, well, if he's dead, I can't find him. He says, if he's very, very poor, I can't find him. If he's very, very wealthy and spends cash, I can't find him. But if he's none of those, he says, I can find him. He's a private investigator. And he found him for me. And you know what he did? He put up the World Wide Web, and he put burlgrey.com. And the son of a bitch, there it was. This guy was smart, okay? So now I'm in touch with Burl Grey, and I found out Burl Grey, he's 74 years old now, because he used to tell me World War II stories. He's 74 years old, he's living on Social Security, and he's going to come out and he's going to water the plants at my condo out in Hawaii in October. And I'll probably meet him then. And ooh. Yeah. So he's going to come out and live there. He's going to relocate. So what a nice story that is. Okay, well, Burl asked questions like this. He's twanging this. So he says, I'm wondering if the tension in my rope is greater than the tension in yours, because he's heavier. Well, let me ask you guys a question. What do you suppose? Would the tension be greater here than in here? Let's suppose you put a scale in here, like that, you know, and you could read the newtons, okay? And read the newtons over here. Which tension do you think would be greater? Say an A or B? Take a guess. Check the person's second. Oh, Burl is heavier than I am. At that time, I weighed. Can you guys do pounds? Yeah. I weighed about 115 pounds, and Burl weighed about 155 pounds. See the bigger arrow? Get it? Okay. Check your neighbor. Time's up. We reasoned that this would be heavier. We just reasoned we could twang it, and it had the higher frequency twang than over here. So that was kind of nice. This is the kind of stuff we talked about from day to day. And then I started walking over toward Burl. I want to get some of his paint. And I'm walking over toward Burl, and Burl says, hey, Hewitt, as you walk closer to me, will my tension get greater? What do you think? We reasoned it would. And our reasoning was this. If this rope were about to break, and it's not breaking, and I come over here and get there too, boom, there's more chance of breaking. And then Burl asked another question. As you walk closer to me, will the tension in your rope get less? What do you think? You think so? That's what we thought too. And we used what we call the principle of exaggeration, which I use now in my teaching. And that was, if I get over here, we both get over here, we could imagine like a seesaw. Maybe we could lean out, and this end would even come up, see? So we reasoned that this tension would get down, go low, less, yeah? And this one will get more. And we can answer that. And we felt good about answering these things. I should say that Burl Grey never went to school either. Never went to college. He went, I'm not sure, he graduated high school. He's one of these guys that was very, very ignorant, but very, very intelligent. And you know there's a difference. How do you feel, by the way, when you realize that many students in your class are more intelligent than you are? You can handle that, can't you? Or you don't deny that. But yeah. But hopefully you're more knowledgeable. Yeah, okay. You're more knowledgeable than they are. Okay. So here's the question we couldn't answer. Burl asked this. Okay, this tension gets more, this gets less. Does this one get less just as much as this one gets more? Let's suppose over here it increases by 50. Will this tension over here decrease by 50? Okay, let me make it more interesting. 50.01. Decrease 50.01. Think about that and check with your neighbor. How many say, yeah, what this one gains, this one will lose? Show of hands. All right. Well, I didn't know the answer and he didn't know the answer. And we wondered about that. And we couldn't figure it out. He was always giving me puzzles. Although those puzzles turns out to be part of kinematics now. The truck is accelerating and the car is decelerating and the light's going to turn, all those kind of things. And the people going on the boat and coming back with 3 boats and 1 cabbage and a pig and all that. We all did those kind of those puzzles. And I used to delight in those, you know. But he'd ask puzzles like this too, all the time. Mental masturbation every day. It was wonderful. Okay? But this one we couldn't answer. This one we couldn't do. And the reason we couldn't do it is because we didn't know the rule. And I found out the rule when I went to prep school. And the rule is a simple one. It's called the equilibrium rule. And you guys know about it. There it is right there. There it is. When I went to prep school, I learned it. And it was the equilibrium. If something's in equilibrium, you can be sure of one thing. All the forces that act on that thing in equilibrium will all balance out to be 0. Sometimes or always. 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 If it's not accelerating, the forces balance out to be 0. So what are the forces in question? Well, there's the force on me, there's the force on Burl. Later on, I learned that the force of the having to do with the weight of the staging can be considered to be concentrated at one point. And so we have three forces acting down. And if those are the only forces that are acting, then these forces will not equal zero. They'll equal what? Mass times acceleration of the system, see? But if in a 0 point, that means there must be some force acting up and some force acting up. And how will these two forces add up compared to these? Same. And that's what it means to say here. So the ups minus the downs, and here's your minus sign, equals 0. And this is the equilibrium rule. And knowing that rule allows one to look at things altogether differently. And here we are at that painting, ignorant of that rule, and we couldn't figure out the answer. And an easier one would be maybe you stand on a bathroom scale and you're looking at your weight, yeah? You stand on two scales, even, Steven, and all of a sudden the weight's down, but you add those two, and what's that equal to? Your weight. Now you lean like this, and you add the two. What's it equal to? See, it's the equilibrium rule, see? But we didn't think about the example. We were answering questions in terms of familiar examples. And by the way, when you're teaching physics, some recent research shows something very, very intriguing. And the research result is this. No students learn any physics whatsoever in your class, unless it is tied to something they already know. So hence the use of analogies. I didn't even realize the strength of my book is analogies until someone told me. So Hewitt, your book is different than others because you just have analogy, 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 analogy. I didn't realize that because that's the way I had to think, because I learned all that stuff when I was late. I remember when I asked I was talking about this with my brother-in-law. My brother-in-law was a fellow that got a bachelor's degree in science and engineering. We had a college degree person in our family. And that person with a college degree could answer this question. He said, do you know about that? He's like the seesaw. Force times distance equals force times distance. That's why it balances. I said, excuse me? Don't you know that? That on a seesaw, how much this is pulled down times this distance will equal this pull times this distance, and that's why it'll balance? I said, no, I didn't know that. I thought that was wonderful, that there's a mathematical relationship that would tell you how a seesaw would balance. He says, well, there are mathematical relationships to everything you're looking at. I've got to go to school. And so I went to school. But anyway, here's a question of the first law of motion, really. A body at rest tends to stay at rest. And if it's rest, that means there's no force in the absence of any forces. So the net force will be 0 on anything that's at rest or moving with uniform speed. Got some practice sheets, gang. And the first practice sheet we have, let's take a look at it. Practice 4.2, Nellie Newton and the ropes. This is page 13 in your book, and let's whip through this together. Nellie weighs 300 newtons, so what do we have up here? 300? What do we have here? 150 and 150? Do you guys have in your school where they have driver education, where they have 2 steering wheels and 2 sets of fuel gauges? And this fuel gauge is half full, and this fuel gauge is half full. How much gas is in the tank? Put a whole bunch of fuel gauges and wow, okay? No, so it's going to be 300 in each, right? And we're neglecting the weight of the pulley. What do we got over here, gang? 150, see? What do we got here?
100.
What do we got here?
Well,
She's pulling down on the table. She can't do that unless the table pushes up on her. So it's still going to be 150 on each, right? What's it going to be over here with all the pulleys? How about bright red pulleys? So you see, there's something to discuss with all of those. And with your students, you could go through and discuss the results of those. And here's a tribute to Burl Grey down here. When Burl the painter stands in the exact middle of the staging, I sent him some of these materials, and he's sort of really, really flattered. He sees that he's become a legend. And what's it going to be over here? Oh, that's getting complicated. Well, this is going to be 1,000, so it's 1,000 take away 170. And what's that? 830? And what's it going to be over here? The bottom. Now you see how when you know the rule, you can do these. And you emphasize to your students, hey, what we're doing here is we're learning the rules of nature. And there's not that many, maybe less than 10 for physics. And if you learn those rules, you will look at nature differently. And I have first-hand experience of that because I didn't know how to do these before. Maybe if someone guided me through, I would discover the rule. But we are presenting the rules of nature when we teach a physics course. And never, never get away from that. It's not humdrum or this or that or see if you can rise to the challenge or let's see how good you are. No, 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 no. Hey, we're going to get an exposure to the rules of nature, and this is the only course that will tell you the rules. And even just telling them and discussing them is enough. That there are rules and that there are consequences for things and all that sort of thing. So here we have 1,000. And more questions. Now we talk about friction. Normal force weight. Do you guys like that normal force, that little n like that, or would you rather have a big N, or would you rather have a F sub n?
I write F sub n.
How many like F sub n? How many like a big N? How many like the little n? Oh, I was talked out of that little n by a reviewer. I said, no, they'll get that mixed up with Newton. And I've regretted it ever since. But it's there. Okay, I like F sub n now because I made a survey. Most people like that. Anyway, when the block pushes on the floor, it can't do that unless the floor pushes on it. And that's Newton's third law. We're getting ahead of ourselves a little bit. So that support force is called the normal force, and there it is. And it turns out the friction force will be proportional to that, directly proportional to the normal force. The friction force directly proportional to that normal force. Double the normal force, you double the friction force. And that's the rule. And the ratio between the friction force and that normal force will be what you call the coefficient of friction. And you get one value for rest, and you get another value for sliding. And I don't distinguish between those two very much, and I don't make a big deal out of it. Because it's not very much physics in that anyway. It turns out friction is horribly complicated. There's a lot of things in physics that are very, very simple, and the more you look into it, the simpler it gets. Friction is not one of them. So when you get to complicated things, you know what I suggest you do? Skim over them and move on. Otherwise, you're going to get caught in some quicksand. But over here, there is an idea that we want to get, and that is that friction is not always equal to mu times n. It means that's the most it can be. Oh, that's different. So we'll make that distinction. And hopefully this sheet will do that. Now the person pulls with vector p, with a pull p, okay? And the block still stays at rest. Well, that means that the friction force must be what, according to our, up here, see? The sideways, the friction force must be equal to p, and the kids can see that. So now we have a situation where equilibrium, you know? So equal to. The net force in the crate is then 0 because it's not accelerating. And that's the rule. If it doesn't accelerate, the net force is 0. Now the pull is increased until the crate begins to move. It's pulled so that it moves with constant velocity across the floor. Constant velocity. What are we trying to show here? It's still in equilibrium. Get it? So we're told now that the net force in the crate is equal to, again, equal to. And you can get into a lot of discussion there, can't you? Constant velocity means acceleration is 0. No acceleration. So the net force in the crate is equal to 0. And there's a lot of physics there. I'm going over this quickly. You'll go over this more carefully. Now, number 4. Pull P is further increased and is now greater than friction force. Now the net force in the crate is greater than 0, right? So acceleration is to the right. And the acceleration is always in the same direction as the net force. Vector, vector. And we won't take time to go through the rest of it right now. Now, we want to make distinctions. Yesterday we talked about vectors and we talked about velocity, and we only talked about velocity. Now we're talking about force. So we have this sheet, and this is page number 15. Number 1 and number 2. Draw a sample of vectors to represent the force of gravity on the ball and draw a sample vector to show the velocity of the ball. You guys do that now, and I'll take a look and see what you're doing. Nice. Oh, nice, 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 nice. Yum, yum. Put arrows at the end there. Yeah. Okay, yeah. Oh, that's nice, that's nice. Now that you've done that, gang, you can do this. Try this, gang. And this is the next time question. A 1 kilogram rock is thrown at 10 meters per second straight upward. No air drag. What's the net force that acts on it when it's halfway to the top of its path? Not at the top. Exactly halfway. Write down what you think the answer is and check with your neighbor. What's the net force acting? No air drag. Halfway to the top. And then compare that to what you did over here in this worksheet. Notice, by the way, the little name at the bottom.
Yeah, how are you?
Now, you know what? I don't have any for you guys in this class. You guys have good ideas. Do you know how hard it is for me to think up these every month? Every month I put these in the Physics Teacher magazine. It's a strain. I need help. And if you guys will help me, let me know some ideas, then I can at least put a little thanks to you and credit you. But hey, it's hard to come up every month with a good idea like this. And the answer? When Howie told me this question, I said, well, it's too easy. He says, Hewitt, it's not too easy. Try it. He said, my students don't think it's too easy. Isn't that a nice one? How many people have intentions, at least, of sometime during the next year sharing some next time question idea with me? Show of hands. Oh, the rest of you people. The rest of you people. When we use force in newtons, mass in kilograms, acceleration will be in meters per second square, then we can say we have the exact relationship. And that's Newton's second law, which is powerful. It explains, for example, why it is that this pen and this kilogram mass will accelerate the same. Here's a heavy rock, here's a light rock. And they're going to accelerate to the ground. Now, what's the rule for acceleration? Isn't it this? And we talk about net force. We talk about net force like this. And you discuss that with your kids. It doesn't take too much time to go through that. And you could pull in such a way the acceleration will be zero, be no force. No force, no acceleration. Force and acceleration directly proportional. And so what's happening? Here, over here we have a big force pulling on this, a small force pulling on this. But the mass of this is huge. The mass of this is small. And what's equal is their accelerations. Here we have it in a transparency like this. These transparencies come with a course. Now, isn't it interesting? What scientist gave to the world the concept of acceleration? Begins with a G. Galileo. What scientist gave to the world, the Western world at least, the concept of inertia, mass? Begin with a G. Galileo. Good, very good. What scientist at that time was well aware of pushes and pulls and forces? Begin with a G. Galileo. What scientist was unable, no, I won't say was unable, what scientist did not connect the three concepts together and left that for someone else to do? Begin with a G. Galileo. Galileo did not connect the three concepts. It took the genius of Isaac Newton to make the connection between these three concepts. So be patient with your kids if they don't get this idea right away. Because Galileo, the master, never did it. You ask Galileo, how come they fall together? He'd have to say DBK. And Isaac Newton is the one that pulled that together. So again, these are very different concepts. Acceleration, time rate of change of motion. Inertia, the tendency of things to resist that acceleration. Forces, the interactions between things that produce those accelerations. Those ideas were not connected. until Newton's second law. And when that came, then, whoo, my God. What did we use to put rockets on the moon? Right there. What do we use now to get the space shuttle on orbit? Right there. That's the one right there. Do you guys do this? What's that say? How do you write density? Do you find density like that?
Yeah.
You do? Don't do it that way, love. Make density like this. Or weight density, I'm saying here. Okay. How do you do Ohm's law? You do it like this? What's that say? Pressure equals current times resistance. Force equals mass times acceleration. I thought a force was a push or a pull. No, it's not. It's a mass times an acceleration. Oh, okay. This doesn't say anything. This says a lot. How do you get acceleration? By pushing. But it depends on what you push on. The amount of acceleration you get is the ratio of force to mass. The amount of density you have is the ratio of mass or weight to volume. And the amount of current you get is the pressure per resistance. So I'll write ratios. I love ratios. They're conceptual. They show you, you have a feel for it. So this one here, we use that for problem solving, F equals ma. But for the concept, write it this way. Newton's was more closely to this than this. Of course, he used momentum. Then you can talk about this. Now we got to say net. So in the absence of air drag, objects will accelerate equally. In fact, when the only force that acts on an object is its weight, we say that object by definition is in free fall, even if it's going up. So when the only force that acts is weight, the object will have an acceleration g. How about if you have something like parachute? Will the acceleration be g or less than g? Okay, it's going to be less than g. Because can we use this rule when air drag is a factor? Yes, we can. Yes, we can. But we've got to look at what we mean by net force. Now what happens here? These parachutes are falling down. Let's make it simple. Let's suppose they start with their chutes initially opened and just drop them, Coney Island style. And let's suppose they're falling at some particular point the same speed. Well, let's look at some vectors here. Okay, we got a weight acting down. Should I put mg or w?
MG.
Little w. Now, as they fall, they'll have an air drag, and the air drag will act in which direction? Up. Air drag, friction, always acts to oppose motion. So if they're moving this way, there'll be an air drag, and let's call it r. Now, if they go in the same speed, the r's will be the same, because they have the same size chute. In fact, the air drag will depend on two things, won't it? It'll depend upon how big the chute is and how fast it's going. Is that right? Okay. So if they go in the same speed, the air drags will be the same. Are both these people accelerating? Ooh. Are both those people accelerating? Answer begins with a Y. Or ends with a P. Got a U in the middle. Yep. Okay. They'll both accelerate because what do we got? What do we have over here? We have this. Now what happens? R is opposed. We're going to say we're going to accelerate down. We're going to accelerate down. So R will oppose the acceleration. And as R builds up to equal W, what happens? They go faster, faster, faster. Pretty soon when they get to be so that this and this are the same, whoops, and this builds up, which parachute is moving faster now? No, not faster. Which parachutist is accelerating? This one or this one? How come this one's not accelerating? And you kind of see what's going on here. See? The air resistance is built up to the weight, and it cancels out, so you have A equals 0 over a number, boom, 0. So she stops accelerating, and she moves down at constant velocity. We say she's terminated her acceleration. We should say she's in a state of TA, terminal acceleration. We don't do that. For whatever reasons, we say TV, terminal velocity. So she's reached her terminal velocity, and this fellow keeps going. So there's an idea that's kind of easy to get across. And in the presence of air, the acceleration will always be less than g. You're taking an airplane ride, and over the intercom, the pilot type yells out things. Okay, gang, we're up in the air. We're 36,000 feet high. We're moving 600 kilometers per hour. The thrust of our jets is 10 to the 5th newtons. We'll be at our destination. Oh, we're moving at constant velocity. We'll be at our destination in 2 more hours. The person sitting next to you says, wow, 600 kilometers per hour, 10 to the 5th newtons of thrust. Whew. Man, we must be splattering against a lot of air. Whew. I wonder what the combined splatterings of all those air molecules against the wings and the fuselage would add up to be. You know, I hear tell there are people who can calculate such things. And you're sitting there and you say, what would you say if I told you you're sitting next to one of those people right now? And delightful person says, oh? And you would say, yes, the combined splatterings of all the molecules, the hitting against the fuselage, the tail, and everything, will add up precisely to be, check your neighbor and see if your neighbor is one of those people right now. How many sitting next to a neighbor who has an answer? And how many sitting next to a neighbor says that answer is 10 to the 5th newtons? All right. You folks in the front row, you got nobody at all? Okay. That back row, my God, was on fire. All right. Okay. See, the rule is what? The little hint was constant velocity. Constant velocity, that means what? All the forces that act on that aircraft, every single one of them combined together, are going to combine to be what? 0. And so he tells you we're thrusting away 10 to the 5th newtons. And you say, gee, at 10 to the 5th newton thrust and we're not gaining any speed? How come we're not gaining any speed? It's like pulling a block across the table. You guys do this. You take a block, you put your spring balance on there and you pull it, you get something like maybe 7 newtons. And you say, guess what the forces of friction must be on that book? But you pull it so it moves constant. And what do your students figure out? 7 newtons, yeah. What if you pull with greater than 7 newtons? What's the book going to do? Accelerate. What if you pull with less than 7 newtons? What's the book going to do? Stay there, see? And when you get up to that 7, then now we get the distinction between static and sliding, but over that, and you get the same thing is true of the aircraft. So anything that's moving without accelerating, equilibrium rule applies. Sum of the forces equals 0. That's that nice rule that Burl Grey didn't know, and I didn't know, which will enable us not to have a tool to be able to look at the world the way we look at it now. So that's an important one. Here's a little practice sheet that gets you ready for that. And we're looking at page number 19. Let's look at 2. Block B is falling. Block A is sliding across. The mass of the system AB is what? 2m? They both have mass m? The force that accelerates that system is the weight of which one? B. Only B? The weight of A doesn't help at all? Nope. If we make a little vector diagram, what do we get? Why am I making this T smaller than the weight of B? Why am I doing that?
You said it accelerates.
It's got to be accelerating. And so that weight had better be bigger than T. Is that right? Yeah. Otherwise, it won't accelerate. It'll either move down at constant speed or it'll hang at rest. Is that right? Sure. Newton's laws holds to every part of a system. And so this t will be the same as this t if the pulley plays no other role than changing the direction of the force, yeah? So the weight of B is mg. And the acceleration of the system is going to be what?
Less than G, less than
It's going to be g over 2. Can that system accelerate at more than g? Less than g? Let's turn the page. Now we have number 3. Now suppose we use the same block, but we have B as a low mass feather or a coin. Compared to the acceleration of the system in the previous page, the acceleration is going to be more or less? Much less. The acceleration of B is constrained. It's constrained because A is pulling back, yeah? Now let's suppose we do the opposite. We let the feather be this part that slides along the top of the table. The acceleration is going to be close to G or close to 0? Close to G, gang? You see the relationship we're building up here? So for these pulley type problems, your answers will always be somewhere between 0 and G, but no way on either side of that. So there's some information that kids can play around with here. Then they'll go into lab, and in lab you'll kind of do this with different masses and different weights. Then we get into vectors. We talked about this briefly already, didn't we? There's a lantern supported by 2 ropes, A and B. In which rope would the tension be greater, A or B? Check your neighbor. Time's up. What would your neighbor say?
A. What, more tension?
Yeah, which is more tension, rope A or B? Make sure that your neighbor gives you some response, even if it's G, I don't know. Okay, I want to show you two ways that I handle this. And one way to handle it is this, to say this. Well, let's say over here there's some tension there. We'll just call it T sub B. And there's some tension in A too. But I know something. The thing that's going to guide me, whoops, is that the sum of the forces on the system will equal 0. See that? So I'm going to say that whatever tension I have there, there'll be a horizontal component down here. That will be this big. All right? Well, if this is true, then there'll have to be as much over here. See? Get it? And that means up here, my tension over here will have to be that big. And so I can see the tension is greater in A. Ain't that nice? Furthermore, I can even tell how big those tensions are compared to the weight. Because I know I have a vertical component here, which would have to be that. And I have a vertical component here, which would have to add it onto that. And I can say, aha, the weight would be greater than either of these tensions. Ain't that nice? So before I have my students go through with the sines and the cosines and all that sort of thing to talk about the sum of the forces and the x equals 0, and put the sines and the cosines right, and the sum of the forces and the y equals 0, and maybe come up with simultaneous equations and all that, I want to be sure that they can see it this way. Do you kind of like that? Would you like to see a better way?
Sure.
Here's a better way, I think. Skip all that stuff. It's complicated. Instead say, well, there's some weight there. And if that thing is hanging there, it can't do that unless it's being held up, because the sum of the forces are equal 0. And I know it's got to be held up with a force that's just as big. Say that big there. And that's got to come as a result of these two forces over here, so make a parallelogram. Here's how big this one is, and here's how big this one is. No coordinate system, no angles, boom, done. Ain't that better? Parallelogram rule. Yum, yum. Some sheets that you don't have in the high school book that are in the college book are this ones. You don't have this. If you want these, I can send them to you. The kids do this, this, then they have to make their own here. They make their own here. Then here's an airplane sailing into the wind. We talked about this a little bit the other day. And they can kind of do that. You know what? The kids enjoy doing this. Then you have challenging questions here. They are challenging. I won't take the time now. Then we have something like this, where the kids say, given two tensions, the result must be like this. Wow, this one here is interesting. And all these are the same. And over here, they're given the weight, and they got to do it the other way around. Say, well, if it's that big, it's got to come down here. They get the tensions here. Make the parallelogram. That big, this big. That big, this big. And the one we had, where we had the weights hanging on there, look at this one here. My God, up to here. They got to come out here. Whew. That's a big force there and a challenge. And then we come to Newton's third law. And Newton's third law is that, hey, I can't touch you without you touching me. You can't touch something without the something touching you back. I can't push on the table without the table pushing me back. I can't push against this without it pushing against me. That's the most I can bend my fingers. If I push against the lamp, more. So what's happening? The lamp is pushing me over here. And you got to get this idea that things can push even if they're not alive. If you push against the wall pushes back on you. The book is on the table. Why isn't it accelerating down? It pushes against the table. It can't do that unless the table pushes against it. And you notice in the book that's developed by a person pushes a spring down. When you push the spring down, can you feel the spring pushing back on you? Well, when you push on a table, the little atoms make up springs too. And so you push the table down, the table will push back on you. And you get this idea that you can't push on something without that something pushing on you. In fact, you get to a whole new idea of explaining forces. Not pushes or pulls, but interactions between one thing and another. So all pushes are interactions between one thing and something else. And that's Newton's third law. The Earth pulls on the moon. It can't do that unless the moon pulls on the Earth. And you know what the law is? The pulls are opposite and equal. And the pull on each is the same. I could ask you, which is longer, going from Vancouver to San Francisco or San Francisco to Vancouver? Same, but different directions. Which pulls harder, the Earth on the moon or the moon on the Earth? Same, but different directions. So you can't push on something without that something pushing back on you. I'm standing on the floor. I can't do that unless the floor pushes up on me. I walk across the room. I push back on the floor. I can't push back on that floor unless the floor pushes forward on me, and hence I move forward. I take a gun and I fire. Boom, the gun kicks. Why is the gun kick? The gun pushed on the bullet. It can't do that unless the bullet pushes on the gun. A rocket going to the moon. A rocket pushes the exhaust. It can't push the exhaust. It can't do it unless the exhaust pushes on it. And so away it goes. And so this is the law of action and reaction, a whole different way to look at forces. I fire a bullet and the bullet's moving. How much force is in the bullet? We had a movie some time ago, Let the Force Be With You. What would be a better physics statement? Let the energy be with you. Because nothing contains force. There's no force in a speeding bullet. It has energy, has momentum, as we'll talk about the day after tomorrow, but no force. Force is something that's an interaction between one thing and another. The bullet will hit the wall. Now there's an interaction. Bullet on wall, wall on bullet, and you have your force pair. So forces always occur in pairs. A whole new way to look at the idea of force. Isaac Newton's final triumph in his three laws. You asked the heavyweight champion of the world, hey, would you like to make $5 million? Yeah. Well, hit this piece of paper with 50 newtons, please. And we'll give you $5 million. $5 million, hit the paper with 50 newtons in midair. Who wins the bet? Nobody can hit this paper with 50 newtons of force. You can't do it. You can't. Now, if you hold it up against a wall, yeah, then you can. Now you're interacting with a wall. But this piece of paper is not capable of a 50 Newton interaction. And then I have my students calculate that in my algebra trig-based course. How much force can you hit the paper with? Well, the speed of the paper will be brought up to from 0 to the speed of the how fast my hand's moving. So you get the delta V. Estimate the delta T. You get the mass of the paper. Figure the F. It's going to be much, much less than 50 newtons. So you can't hit this paper any harder than the paper will hit you back. In a social commentary, and that is Gandhi. You can't push them if they can't push you any harder than you can push them. An interaction requires two. And so you can't punch your way out of a paper bag. Newton's third law. You can't hit that paper any harder than the paper will hit you. You see a car moving down the road, right? What's pushing the car? The road. Have your kids say that. Say, hey, Mom and Dad, you see this? See the car going down the road there? Guess what's pushing the car along? The road. That's why you want good roads. The wheel pushes the road. The road pushes the wheel. And the wheel's attached to the car. Rocket pushes gas. Gas pushes rocket. Earth pulls ball. Ball pulls earth. Action, reaction. Now at City College, when we hire candidates, we like to see how they perform in front of students. And we always have the student ask a question. It's a shill in the class. And he asks this question. Hey, if I take an object and I let it go, falls. It's a force acting on it. Accelerates. What's the reaction to that force? Now we know they can't answer it. And we want to see what they do. Could you guys answer that? Let's try it again. I'll use a different color. You want to get a job at City College? Student says, there's a force acting on it because it accelerates. What's the reaction to the force? I don't care if they get 3 PhDs. They won't answer it. Because the question's too fuzzy. The answer you get depends upon the way the question's asked. Let's suppose the student says, when you let this go, the whole world pulls down on the pen. So it accelerates. What's the reaction to the world pulling down on the pen? The pen pulling up on the world. So the question is phrased very nicely, isn't it? It's like the monks in the prayer room. They're smoking. And the friar comes in and says, you can't, that's a sacrilege to smoke in here. They say, well, what if we get permission from the bishop? It's okay. So they write a letter to the bishop. Is it okay to smoke in the prayer room? What's he going to say? No way, it's a sacrilege. Let's suppose they ask the question differently. Is it okay to pray while we're smoking? Yes. So the way you ask a question is the kind of answer you give. So Newton's third law is a lot of fun. It's very, very important. It has a whole new way of looking at what force is. Got it? Look at our first comic strip, Horse Sense. Farmer says to the horse, giddy up, pull the cart so we can go. Horse says, why should I? The force I pull will be the force that pulls on me. The forces will cancel out, be no force, so why don't we stay? And you got one answer given here, and the horse and the farmer could say, hey, look, I know this. That if you provide a net force on me, I'll divide that by my mass, and I'll get an acceleration, and that's the end of the story. And it is. And so the farmer could say, I don't care about you. And the horse will say, yeah, but how about me? It's pulling back on me. The horse says, I don't care about you. I care about me, and I care about getting my groceries and my things to market. You pull on me, I go. Now what's happening in that case is the farmer is taking the system off the cart. Let's look at the forces that act. The horse does pull on the cart. And say there's negligible force down in here. Negligible. So there we go. Now what other forces act? There's a force of gravity acting down. So normal force acting up, they cancel out. In this particular direction here, there's a force, and there it is. Divide that force by the mass of the cart, and away it goes. Done. The horse says, how about me? Well, let's look at the horse. From the horse's point of view, what's the act? Look, there's a force pulling back on the horse. Same force. Any other forces acting on the horse? Yeah. This force of gravity, it's a normal force. Any other forces acting on the horse? Is the horse pushing against the ground? But the horse can't do that. The horse cannot push against the ground unless the ground pushes against the horse. Got to be a to and a fro. So the horse pushes against the ground this way. Shall I make a vector back here? No, that's the vector on the ground. I'll make a vector for the force that acts on the horse. So he pushes the ground back, and the ground pushes the horse forward. Now, if this force is greater than that force, what will happen to the horse? It will accelerate. Okay? What if this force is equal to this force? The horse will either stay at rest or move at constant speed. So there's the system of the horse. Then we can take the grand system. So system, system. Who's got the system? Remember the game you played when you were a kid? Button, button. Who's got the button? This is system, system. Where's the system? System of both. These forces cancel out in that system. So in the system of horse and cart, these don't act. The only force that acts is this one here. And that force, divided by the mass of the system, will give you the acceleration of the system. And if that's equal to the forces of friction, air drag, then they'll move at constant speed. Yum yum? As the textbook says here, this is a problem that people in graduate school have difficulty with. Ask this in graduate oral exams, and it's very easy to get confused, and you got to do a lot of thinking before you start to teach it. You got three systems, either this one, put together. We could talk about the same, we'll talk about the same thing pretty shortly with terms of balls. There's a ball moving over here. It hits. When it hits, after it hits, this one stays at rest, and this one moves. And you can kind of look at that in terms of systems too. Let's take the system of only this ball. Now it's moving with velocity v. Does it continue moving with velocity v? Yes, because there's no force at all acting in the system this way here. All of a sudden it hits here, and boom, there's a force acting on it. Here it is. And that force does what? Decelerates the system. Now, it decelerates it, brings it to rest, and here is at rest. And now when it leaves, there's no force acting, so a body at rest tends to stay at rest. Or I could say, let's let this be the system. It's at rest, stays at rest. All of a sudden now, it's hit with force, so it accelerates. So it's moving, and when it's over here, no force, it's moving. Or I can take this be the system. What's the force acting there? Nothing. So whatever motion it has, well, we get momentum. Over here, even here, there's no force because they're equal and opposite. And over here, no force. So really, there's been no change in what happens to the system. This one I love. How does a sailboat sail into the wind? This is a nice one, and let's see if we can understand it. And what I do in my classroom with this, let me just describe my little demo. It's before the time of air tracks. And my little demo is that of a little cart, a little laboratory cart, and on the cart I have a little block of 2x4. And the 2x4 has some slots in it. I could just draw it up here and show you. and it's mounted on a little cart here. And you got the little wheels here, okay? And now on the 2x4 I have a slot cut like this. Slot cut like this. Slot cut like this. Slot cut like this. These are slots cut right into the wood, see? Now I can put a fan. I can put a piece of aluminum. And I could put a fan in back here. And when I put the fan back here, no one's surprised to see. Of course, this is all blocked down. No one's surprised to see it going along. And I can put the fan in at an angle. And no one's surprised to see it going along. And then I can put the fan in front of it when it's at an angle, and everyone is enormously surprised to see the boat moving right into the wind. That is a nice one. Honey, nobody's asleep. Everyone's paying attention. How can be such a thing? All right? And I want to guide them through to see if they can see that if they understand vectors, they can get it. So let's us go through this together right now. If you guys get this one in your thing here, let's go through together. Number A, draw the components on the sketch. First of all, we'll get the thing here. Can you guys do that? Can you make a little dotted line like this? Can you make a little rectangle? And can you make your force out like this? And a force like this? And then we ask questions. Which component is larger? The one that's perpendicular? Yeah, the one due to gravity, yeah. This is a top view, gang, top view. Okay. So the one that's perpendicular. Which component produces acceleration? The one along the track. Now, so far, will your slowest students be able to do that? What would be the effect of pulling on the rope if it were perpendicular to the track? Let's suppose the rope would just pull down like this, and it weren't pulled like that at all. What would happen?
It'd tip over, yeah.
It'd tip over, but it wouldn't move. See these things up here? I have these in my room too. And I can put a string on there. And if I put a string on here and pull this way, guess which way it goes? It goes that way. Let's suppose I pull the string this way, guess which way it goes? It goes that way. Let's suppose I pull like this, which way does it go? Still that way. Like this. That way. How about like this? It's not going to move. It's not going to scoot this back and forth along the track. This is constrained to move. I've got to pull over here, and you can see the component thing working there, can't you? And same thing over here. So it wouldn't move at all if you pulled it in that direction. No acceleration. Now we have a boat being with the broadside here, force acting straight down. Why is the position of the sail useless for propelling the boat along the forward direction? And relate this to the problem above. And there's simply no component along the direction of motion. This is just like pulling the track perpendicular, isn't it? So this boat, gang, is not going to move by virtue of that force, all right? Now, let's suppose we tip the sail, as we have over here in B. Now, sketch the components of force along the dotted lines. Do that right now, gang. Will the boat move in a forward direction? Yes or no? Answer ends with a P. Yep. It'll move because there's a force component in that direction, yeah? So far, so good? Understandable? When I have my sail top view here, if I have some wind coming in, hitting like this, the molecules of the wind, boom, bounce off and give me a force like this. If I have a coin right here, and I take another coin and bounce it off, and the coin bounces like that, the direction of this coin will be like that. And then you can get into some momentum to describe that too if you want. But here's the interesting thing. If my wind comes in and whoosh, bounces off like that, I'll get my force perpendicular. But if my wind came down like this and bounced off like this, what difference would I have? The sail doesn't know the difference. And if I send this coin in like this or send this coin in like this, either way, it'll bounce over here. No difference which way the ball's going. You could back it up.